Hello, I am Ahmad, and in this video we are going to continue the last example of which we tried to calculate what is the yielding force applied to a rod in the distance of 400 millimeter from one support and 800 millimeter from the other support. In this example, we are going to reload or remove the load from the system and check out what would be the permanent deformation or what would be the residual stress in the elements. Let's do so. In the previous example, we went through the calculation of the load that can be applied to this system. At point A, we have the fixed support, and also at point B, we have another fixed support. As a result, the element with the material of like brass with the modulus of elasticity 100 gigapascal and the yielding stress of 180 megapascal is assumed to be a elastic, perfectly plastic material. And we can recall the load and also maximum force that can be applied to this system. It was 254 in maximum, of which 127 kilonewton is the yielding of each rod. As a result, it was 254 kilonewton. At the end, we proposed to apply the load up to 160 kilonewton and then remove it to check what would happen to the system. And in the second one, we are going to apply 200 kilonewton load as force P and check when we remove it, what would happen. So let's have these three graphs, point A, point C, and point B, and the force is applied at point C towards left. 400 millimeter and 800 millimeter. And also E was 100 gigapascal, sigma yield 180 megapascal, and the diameter of the rod was assumed to be 30 millimeter. Sigma and epsilon 180, 0.0018 was the epsilon y. And this is how it looks like after applying the load. We can increase the load up to 254 kilonewton, and then the system will be a mechanism, meaning that it cannot hold the load and it will be completely plastic. Now, the first example is to assume if the force is going to be 160 kilonewton, what would happen? So in this case, if the load is 160 kilonewton, this is less than 190.5 kilonewton that we calculated earlier. As a result, this load is less than the total load that can be applied until one element, which was AC, to be plastic. In this case, two rods are loaded less than their yielding load. As a result, the system is elastic. So removing the load would result in coming back to the original length of the system, meaning that all members are in elastic phase. We can also sketch what would happen to each element. If you remember, AX plus BX was supposed to be P, and also we had the relation between these two in the elastic phase. AX was going to be 2 times BX. So now we have the load, which is 160 kilonewton, and AX plus BX will be 160, and AX is 2BX. As a result, 3BX will be 160, and then BX will be 53.3 kilonewton. Consequently, AX will be 106.6. As we can see, AX and BX are both less than 127 kilonewton, which was yielding force. We can also calculate the stress in each element. Sigma at AC will be AX divided by area, which is 106.6 kilonewton divided by pi, 30 millimeter square divided by 4. So 151 megapascal, which is less than 180 megapascal. Also in the other element BC, it is BX divided by area, 53.3 kilonewton divided by pi, 30 millimeter square divided by 4, it will be 75.5. Still smaller than 180 megapascal. Also, we can calculate what is the strain and deformation for each member. Strain in AC will be sigma divided by modulus of elasticity, which is 151 megapascal divided by 100 gigapascal. So it will be 151 divided by 100 gigapascal, so 0.015, and it's less than epsilon y, which is 0.0018. Also, we can calculate deformation for AC, which is epsilon times L. Epsilon is 0.0015 times 400 millimeter, 0.6 millimeter. Similarly, in the other rod, epsilon BC will be sigma BC divided by E, which is 75.5 megapascal divided by 100 gigapascal, and it will be 0.00075, and it is less than epsilon y. Delta BC will be epsilon times L, 0.00075 times 800 millimeter. So surely it should be 0.6 millimeter. And as far as both members are in the elastic phase, if we remove the load, it will come back to its original length. In other words, we can summarize this example. A and B, and this point is 800 millimeter, 400 millimeter, and we apply the load up to 160 megapascal, and point C would move towards the left for 0.6 millimeter. And in the next phase, when we remove the load, it will come back to its original length. So there will not be any permanent deformation, and as far as the load is removed and the elements came back to its original position, then the stress inside each element will be 0. So after unloading, sigma in AC and sigma in BC will be 0, and delta C will be 0. Now, for the next phase, when we apply the load to be more than the first element yielding load, which was 190.5 here. So we assume that the load is going to be 220. And we know that this load is greater than the yielding of one element. In that case, we would expect that the system will be under a permanent deformation because the load is greater than one of the elements become yield. So before we continue, it is better if we have a look on the material behavior in loading and unloading. Assume that we have a homogeneous material with the same behavior in tension and compression, epsilon and sigma. The maximum value for the sigma is called sigma y, and the corresponding strain is epsilon y. We assume that we are not talking about buckling. We are just talking about the material behavior if there is not any kind of buckling in compression. The positive side is usually tension and the other side is compression. Assume that we assigned load to this system until its stress, actual stress is very close to sigma y. So it is loaded and here we stop. Now if we remove the load, better to say that if we reverse the load. So let's have a look on one element. At point B, and we apply the load, increase the load. And now let's assume we keep this load at its level. That results in the stress inside the element will be very close to yielding point or sigma y. And now I apply another load in the other direction as a reverse loading. As far as it was not yield with the force P, so it starts to come back to its original position. And now the capacity to be in linear phase is greater than sigma y, because if you apply P star the same value as P, then it will be in the zero position, or the deformation will be zero after P star is exactly the same value of P. And now we are in this position if P star is going to be same as P. Now we have again the same value of P to apply in compression side to come to the other point. So it means that if you apply the force P, you will have, if the material is homogeneous and its behavior is the same in compression and tension. For example, in concrete, we do not have this type of behavior. But in steel, if it is not susceptible to any buckling, we can achieve this value. If you apply the force up to the stress in the element becomes sigma y, then we have 2 times of P capacity that the material is behaving linear. So let's have some numbers before we continue for the question. Sigma y is 180 megapascal and epsilon y is 0.0018. The same is for the compression side. Now we apply the load. And in here we can say that for this example with diameter of 30 millimeter, the maximum force or the F in the yielding point was 127 kilonewton. So it means that if P is slightly less than 127 kilonewton and you load it, then you have twice of this 127 kilonewton that the material is behaving elastic. 127 kilonewton coming back to its original length or original point, and then 127 kilonewton more to become plastic in the opposite direction. So if P in the loading from 0 position is 127 kilonewton, then in reverse loading, the element will be elastic with the capacity of 2 times 127 kilonewton. So this is the concept. It is applied to any type of reverse loading in torsion, in bending. As I said, if the material is homogeneous and the behavior of material is the same in tension and compression. Now we can continue to solve our question. So now force in this element is going to be 220 kilonewton. And from the P graph, we can see that we are somewhere here. As far as it is greater than 190.5, so 220 would lead into the AC element become plastic. You can see that we are somewhere here. Let's call it number 3. And it's between 1 and 2. So here in AC graph, we are somewhere here. Number 3. And in BC graph, we are somewhere here. We can see that in BC, still we are in the elastic phase. But in AC element, we are in the plastic phase. Now we have to check if we put the same load in the other direction with 220 kilonewton, what would happen? So the easiest way to solve this type of question and understand how it works is that keep the load as it is. A, B, point C, and let's keep the original load, which was 220 kilonewton. And now start to apply the same load in the opposite direction. It's reverse loading. In the initial loading of 220 kilonewton, we know that element AC will be completely plastic, and BC is still in the elastic phase. So I will write down loading E equals to 220 kilonewton. So elastic relation between AX and BX is not valid anymore. It means that we cannot write delta C is FL over AE. One would think that, okay, I do not know how to do it. Let's start to assume that still we don't know if this 220 kilonewton is greater than the elastic load of one of the members. So let's solve from the beginning with the simple assumption AX plus BX is E, and now AX should be 2 times BX. So if you apply this to the given equation, 3bx will be 220 kilonewton, and as a result, bx will be 73.3 kilonewton. And then we can summarize that ax will be 146.6 kilonewton. bx is less than 127 kilonewton, and this is fine. But if we look at ax, it is greater than 127. And this is greater than the yielding force of the element, so this is not fine. As a result, E equals to 220 kilonewton shows that the system is not elastic for all members. Later on, we will work only with the graph to understand how it works. Now, we know that all of the elements become yield. As a result, we say that, okay, AX is maximum 127 kilonewton. AX plus BX is going to be P, which is 220 kilonewton. And as a result, BX will be 220 minus 127 kilonewton, which is 93 kilonewton. And this is less than 127 kilonewton, and this is fine. So in the loading condition, the load in AC will be 127 and the rest will be transferred to BC. And as far as AX is now plastic, we cannot use the equation of delta FL over AE for calculation of deformation at point C. But we know that AC and BC are one entity, and wherever C goes, it's a single node. As far as BC element is still in elastic phase, we can use the deformation at point C. So F B C times L divided by A E, which is 93 kilonewton times 800 millimeter divided by pi 30 millimeter square divided by 4 times 100 gigapascal. So this value will be 105 millimeter. We can check this calculation also from our graphs. So the value of load here is 93 kilonewton. And here we can calculate what is the deformation. So 127 kilonewton divided by 1.44 millimeter is as same as 93 kilonewton divided by delta. And delta from this equation will be 93 times 1.44 divided by 127, which is 1.05. So this is only for loading. Also, you can use the same principle from the other graph, from here. If we want to calculate from this graph, we can write down that 254 minus 190.5 kilonewton divided by 1.44 minus 0.72 millimeter will be as same as 220 minus 190.5 divided by delta minus 0.72. So from here we can calculate delta, which is 1.05 millimeter. So we can see that it doesn't matter from which graph we are using, except graph AC. In graph AC, as far as the AC element is now plastic, so we cannot calculate where this point C will be from that graph. It means that the elastic equation is not applied. Now, reverse loading or removing the load from the system. .05 millimeter, and also in this case we are here 93 kilonewton, and the corresponding deformation is 105. And from this graph also we are here 220 kilonewton with the corresponding value of 1.05 millimeter. So now if you apply the reverse loading, the capacity of AC is not 127 for the elastic phase. Now it is 254 kilonewton. As a result, again, we assume that the elastic is applied. So reverse loading. Now the capacity of AC is 2 times 127 kilonewton, which is 254 kilonewton. If we are interested in the capacity of BC, is 93 kilonewton plus 127 kilonewton. It is loaded up to 93 kilonewton, and it has the capacity to, in the compression side, up to 127. So it will be 220 kilonewton. From the graph also we can see, if we start from here, then it can come as elastic material up to this point. And from here, it can come to this point. So we have 93 plus 127. The other side, we have 127 plus 120. It means that AC can take up to 254 kilonewton in the reverse loading, and up to 254 kilonewton, it will be in elastic phase. Partially in compression, partially in tension. And element BC will be in elastic phase up to 220 kilonewton load. So in the reverse loading, we assume that elastic analysis is valid. As a result, AX will be 2 times BX. And AX plus BX will be the magnitude of the reverse loading, which is 220 kilonewton. From here, so 3BX will be 220 kilonewton, or BX will be 73.3 kilonewton, and consequently AX will be 2 times BX, which is 146.6 kilonewton. Both of them are in this phase less than their maximum elastic capacity. So the elastic capacity here is 220 kilonewton. And here, elastic capacity is 254. So both are fine. And we can say that in the reverse loading, BC will take 73 kilonewton and AC will take 146. So loading FAC was minus, it was in compression, minus 127 kilonewton, and FBC was plus 93 kilonewton. And in reverse loading, AC is 146.6 kilonewton and BC is 73.3 kilonewton. So you can sum these two together to apply that there is no load between these two elements anymore. So FAC final stage after removal of the load will be minus 127 kilonewton plus 146.6, which is 19.6 kilonewton. And FBC final should be exactly the same. It should be in equilibrium. So plus 93 kilonewton. Right here it was in compression. Minus 73 in the reverse loading. Minus 73.3 kilonewton, which is 19.7. So to be exact, it will be 19.66 and the other one will be 19.66. So the reason is the approximation of with one significant value. So this is the final load in each element when we do not have any force. In other words, both elements will be in tension after unloading the structure. Now we want to calculate what is the residual stress and also what is the permanent deformation. If we look at the force and deformation of element BC, the maximum load was 127 kilonewton and the maximum deformation was 1.44 millimeter. And we loaded up to 93 and the deformation reached to 1.05 millimeter. After that, we unloaded the structure and the residual force inside the element is now 19.6 kilonewton or 7. To be exact, 67 kilonewton. And now we want to calculate what is the deformation here. We can write the trigonometry relation. 127 kilonewton divided by 1.44 millimeter should be as same as 19.67 kilonewton divided by delta final. And from here, delta final will be 19.67 times 1.44 divided by 127, which is 0.22 millimeter. And as we can see, it is elongated. It means that point C is moving to the left. We can also check this value from the other graphs. For example, if we bring our sketch for the force P. So in the reverse loading, it will come back to being reloaded, but by the slope of the elastic side. I can sketch it outside of this graph. So here is the main line from 0 to 190.5, and the corresponding deformation here was 0.72 millimeter. After that, it was something like, it should be exactly twice. So the deformation here is 1.44 millimeter, and the load is 254. And now our situation after loading the system is 220 kilonewton. And the corresponding deformation is in 1.05 millimeter. Now, if you want to work with this graph, you just need to sketch a parallel line to the elastic side, and this will be delta permanent. For calculation of this delta, I can say that this is point O, this is point A, here is point B, what else? Point C and point D. So BD divided by AB is parallel to OC. It has the same slope, so it will be, okay, here we have point E as well. So it will be as same as CE divided by OE. So BD is 220 kilonewton. AB is unknown. CE is 190.5 kilonewton. And OE is 0.72 millimeter. From here, we can calculate the distance or the length of AB, 220 times 0.72 divided by 190.5. So it is 0.832 millimeter. As a result, OA, which represents the deformation, will be OE or OB minus AB. OB is 1.05 millimeter minus 0.832 millimeter, and delta will be 105 minus this answer, 0.22 millimeter. The same value as we calculated from the other, or from BC element. And also we can calculate the residual stress in each element. So after unloading, F inside AC will be 19.67 kilonewton. Also in BC, it will be 19.67 kilonewton. So the stress, as far as they are with the same diameter, same material, will be 19.67 kilonewton divided by pi. 30 millimeter square divided by 4, the same value for the other one, 28 megapascal. Let's cross-check these values. You can solve this problem with many. There are plenty of ways to solve it. So in the loading, force in AC was 127 kilonewton. As a result, sigma was minus 108 80 megapascal. It reached to its yielding limit. And in BC, the load was 93 kilonewton. So sigma in BC was 93 kilonewton divided by pi 30 millimeter square divided by 4. So it will be 131.6 megapascal. And in the reloading, FAC was in tension 146.6 kilonewton, and FBC was in compression, which was 73.3 kilonewton. So sigma AC, sigma BC, 207.5 megapascal. So indeed it is greater than 180, but still it is in elastic phase because it is reversing. It was fully compression, and up to being fully tension, there are 2 times sigma y capacity. So it means that the limit is 360, 2 times 180 megapascal. And for BC, it is half of that, which is 103.75. As far as the load is in the other direction, this is positive in tension, this is negative in compression. And if we sum these two, sigma final for element AC should be 180 in compression plus 207.5 megapascal in tension. So 207.5 minus 180 is 27.5, which is almost 28 megapascal that we calculated earlier. Also, sigma final for member BC will be 131.6 megapascal positive minus 103.75 megapascal, which is 20, almost 27, 26, almost 27, or we can say that it's very close to 28. The reason to have not exactly the same value is for rounding the numbers, but it should be exactly the same. If you go with more accurate calculation, it will be pretty the same. Now it is also worthy if we check from the element AC how it looks like from that element. Force versus displacement, kilonewton, millimeter. And here is 127 kilonewton corresponding to 0.72 millimeter. The same in the other direction, 0.72 millimeter and 127 kilonewton. And this is 1.44 from the earlier. And we loaded this system up to 1.05 somewhere here. Now when we start to unloading this system, it will be in the elastic phase. So the slope of reverse loading will be exactly parallel to the elasticity line or elastic line. This is the reverse loading of the system. So now we calculated, and the load in this system will be 19.67. We calculated the load and it was 19.67 in this member. So if we come to 19.7, it will be somewhere here, 19.67 kilonewton. And this value is correspond to the relevant load. So now we are looking for this delta. Again, we can name these points with some parameters. Assume this is A, and here this is B. This point is C. So what we know that BC divided by AC is parallel to the main line, which is O, D, and E. So it will be with the same slope as OD, or it will be DE divided by OE. We know BC is 127 plus 19.67 kilonewton divided by AC equals to DE, which is 127 divided by 0.72. As a result, AC will be 127 plus 19.67 times 0.72 divided by 127. So 0.83. Now, delta can be calculated as, if this point is F and this point is G, so it will be OF minus FG. We know that FG is the same as AC, so it will be OF minus AC. OF is 1.05 millimeter minus, we calculated AC and it was 0.83 millimeter. 105 minus 83 will be 0.22 millimeter. And here is the final position. We can just sketch the situation. To summarize, loading of the element, phase 1, E between 0 and 119.5 kilonewton. So both are in elastic phase, AC and BC. So in this phase, if P becomes 190.5, AC will take 127 kilonewton and BC will take 63.5 kilonewton. After that, we increase the load up to 220 kilonewton. In this phase, AC remains unchanged. It cannot be increased. And BC will take the entire load after that, so 93 kilonewton. And now we start to reloading. From 220 kilonewton to P equals to 0. So in this phase, there will be a residual force inside the elements, which is in tension. So FAC equals to FBC, and it will be 19.67 kilonewton, and it's in tension. But the permanent deformation of C is 0.22 millimeter to the left. So in the next example, I will model the same rod with the same material, for example in RFM, and we will see how we can model this type of structures in a FEM software and how it looks like. Yes, in this video we went through the calculation of plastic or permanent plastic deformation for a rod which is loaded beyond its elastic limit. So in this example, we calculated the residual stress inside the element as well as the permanent deformation after unloading or reverse loading. Thank you for watching and see you next time. Bye.